There is a machine on a mountaintop in Chile that was never meant to take a single beautiful picture. It was built to do something almost nobody expected a telescope to do. Watch, not stare, not focus. Watch the same patch of sky over and over, thousands of times, hunting for the one thing that changed since the last look. It's called the Vera Rubin Observatory, and in its very first months of operation, before its real mission had even officially started, it found things that shouldn't have been findable. A river of stars, longer than our entire galaxy is wide. An asteroid spinning so fast it should be flying apart in real time. A star in a neighboring galaxy that may have simply vanished with no explosion, no warning, nothing. And visitors, actual physical objects, that came from other solar systems entirely and passed silently through our own. By the end of this video, you're going to understand why scientists are calling this the most disturbing first year any telescope has ever had. Not because it's broken, because it's working exactly as designed. And what it's designed to do is catch the sky in the act of changing. Sitting high in the Atacama Desert, under some of the darkest, driest skies left on Earth, Rubin houses the largest digital camera ever built for astronomy. But the camera isn't really the story. The story is what the observatory does with it. Most telescopes, even famous ones, work by picking a target. Astronomers choose a galaxy, a nebula, a patch of deep space, and they point the instrument at it for hours, sometimes days, squeezing out every photon of light they can. That's how Hubble gave us its iconic, impossibly detailed images. That's how James Webb pulled infrared light out of the early universe, letting us see galaxies as they looked billions of years ago. Rubin doesn't do that. Rubin does something almost the opposite. Its mission has a formal name, the Legacy Survey of Space and Time. And that name sounds bureaucratic, almost boring. It is not boring. What it actually means is this: Rubin is filming a 10-year movie of the entire visible southern sky. Every few nights it sweeps across the whole sky it can see from horizon to horizon and takes a full inventory. Then it comes back a few nights later and does it again and again and again for a decade. Every time it returns, software compares the new image against everything that came before. A dot that wasn't there, a star that got brighter, a galaxy that flared, an object that used to be visible and now simply isn't. Each one of those differences triggers an alert. In its earliest test runs, before the survey had even truly begun, Rubin was already generating hundreds of thousands of alerts in a single night. Once it's running at full capacity, that number is expected to climb into the millions. Every single night, the observatory flagging millions of things in the sky that are different from how they looked before. Think about what that actually means. For all of human history, the night sky has felt fixed. Stars appear to sit in the same place year after year. Constellations look eternal. The universe, to the naked eye, looks like the one truly permanent thing we have. Rubin is quietly proving that was always an illusion. The sky was never still. We just never had a machine capable of noticing the motion. On June 23, 2025, the observatory released its first real images to the public, and one of them broke people's sense of scale entirely. It was a single composite photograph of the Virgo cluster, and packed into that one frame were roughly 10 million galaxies. Not stars, galaxies. Each one of those 10 million points of light is itself a collection of billions of stars, along with their planets, their black holes, their nebulae, entire unexplored architectures of matter compressed down into a single speck in one photograph. If you tried to look at every galaxy in that image for just 1 second each, without stopping, without sleeping, it would take you months just to glance at each one. And that image was a fraction, a sliver of what Rubin is ultimately going to capture over its 10-year run. Scientists expect the total tally of galaxies observed to reach into the billions. But the headline number wasn't even the strangest part of that first release. Buried inside the data was something nobody had catalogued before. A stellar stream, a long, faint ribbon of stars, being torn away from a spiral galaxy called Messier 61. That stream stretched roughly 163,000 light years. For context, that's wider than the diameter of our own Milky Way. And it had been sitting there, undetected, until an instrument finally had the width, the sensitivity, and the patience to actually see it. A stellar stream isn't just a pretty structure. It's a scene of violence, frozen in time. It means something. A smaller galaxy, a star cluster, wandered too close to a bigger one and got shredded by gravity. Its stars stretched into a long trailing wound across space. These streams are essentially fossils. They record how galaxies grow by consuming each other, how invisible dark matter sculpts the motion of visible stars, and how the largest structures in the universe get built through slow-motion collisions that take hundreds of millions of years to play out. And Rubin found one of these fossils, larger than our entire galaxy, on essentially its first real look at the sky. Then came the asteroids. In just its opening stretch of operations, again, before the full survey had formally begun, Rubin discovered more than 11,000 new asteroids. On its own, that would already be a historic haul. But it's a preview of something much bigger. Once the observatory is running at full strength, scientists expect it to find around 1 million previously unknown asteroids in its first year alone, a number that roughly matches everything humanity has catalogued over the past 2 centuries combined. In other words, one telescope in 12 months could double 200 years of asteroid discovery. That matters more than it might sound. Asteroids aren't just rubble. They're time capsules from the early solar system, carrying physical evidence of how planets formed, how orbits shifted, how collisions shaped the neighborhood we live in. Some are harmless, some cross uncomfortably close to Earth's orbit, and some are just strange enough to make scientists stop and ask real questions. One object in particular, designated 2025 MN45, is doing exactly that. It's enormous, nearly twice the height of the Empire State Building. But its size isn't what's unsettling. Its spin is. This object completes a full rotation once every 1 minute and 53 seconds. For something that large, that speed is extreme. Extreme enough that basic physics says it should be tearing itself apart. A loosely bound, rubble pile asteroid spinning that fast should be shedding material. Cracking, coming undone. It isn't. It's still there, still intact, still spinning. Nobody has a confirmed explanation. Maybe its internal structure is stronger than the typical rubble pile model assumes. Maybe its composition is different from what scientists expect for an object its size. Maybe there's a formation process at work that hasn't been fully modeled yet. What's clear is that Rubin isn't just adding numbers to an asteroid catalog. It's turning up objects that don't fit the rules we thought we understood. And this is only the opening batch. Most asteroid surveys before Rubin worked the way most telescopes work. Pick a patch of sky, stare at it, move on. Rubin's approach is fundamentally different because it isn't trying to find asteroids in a single pass. It's trying to catch them moving, night after night, across the entire visible sky at once. That's exactly the kind of survey needed to catch fast, small, dim objects that a narrower search would simply miss. Some of what it finds will be scientifically interesting and nothing more. But some of it, like 2025 MN45, is going to keep raising uncomfortable questions about what these objects are actually made of and how many more of them are quietly breaking the same rules without anyone noticing yet. Asteroids are only one category of small object Rubin is built to catch. There's a rarer, stranger class of visitor it's also hunting for. Interstellar objects, fragments of other solar systems entirely, passing briefly through ours before continuing on into deep space, never to return. In all of recorded history, humanity has confirmed only a small handful of these. The most famous, Oumuamua, became a sensation because of its bizarre shape and its unexplained acceleration as it left the solar system. A few more have followed since. Each one is essentially a tiny, uninvited sample of another star system, material that formed somewhere else entirely, shaped by different chemistry, a different star, a different history, briefly close enough for us to study before it's gone forever. We can't chase these objects down. We can't send a probe fast enough to catch most of them. Our entire window to study them is whatever time we have between spotting them and watching them leave. Rubin's constant, repeated scanning of the sky makes it one of the best tools ever built for catching these visitors early enough to actually learn something. Scientists estimate it could find anywhere from a handful to potentially dozens or more interstellar objects over the course of its survey, a number that would dwarf everything found before it. That matters because these objects are, in a very real sense, free samples from other star systems. We can't travel to another solar system to study how its planets or asteroid belts formed. But if a piece of that system happens to drift close enough to our own, and we're actually watching when it does, we get a direct physical look at material that was never shaped by our sun. Every interstellar object that's been caught so far has raised more questions than it's answered. About shape, about composition, about why some of them seem to accelerate in ways that don't perfectly match simple gravity and outgassing. With Rubin scanning the entire sky every few nights instead of relying on a lucky, isolated observation, the odds of catching the next one early, while there's still time to actually study it, go up dramatically. Here's where the story gets genuinely eerie. Everyone knows what a supernova looks like, at least conceptually. A massive star reaches the end of its life and detonates, briefly outshining its entire host galaxy. It's violent, it's bright, and it announces itself across enormous distances. But there's a rarer, quieter version of stellar death that theorists have argued about for decades. The failed supernova. Instead of exploding outward, the star's core collapses directly inward, straight into a black hole, with no explosion, no flash, no warning shot bright enough to catch anyone's attention. One moment there's a star. The next, there's nothing. No fireworks, just absence. The problem with confirming this ever happens is that it's defined entirely by something not being there anymore. You're not looking for a new light in the sky. You're looking for an old light that quietly went out. That's an almost impossible thing to catch, unless you have a machine that remembers exactly what the sky looked like before. That's precisely what Rubin is built for. Because it repeatedly images the same regions of sky, it can directly compare what a location looked like months or years ago against what it looks like now. And in its early data, astronomers flagged a candidate in the Andromeda galaxy, roughly 2.5 million light-years away, a star that appears to have simply stopped existing. If that candidate is confirmed, it would be direct evidence that some massive stars don't go out in a blaze of light. They just collapse, silently into black holes that form without ever announcing themselves. And the implication of that is bigger than one star. If some stellar collapses genuinely happen without a visible explosion, then there are almost certainly more black holes scattered across the universe than we've ever accounted for, because the ones that formed quietly were never bright enough for us to notice in the first place. Underneath every one of these discoveries is the real target of the entire mission: the invisible universe. Everything we can directly observe, every star, planet, galaxy, and asteroid, makes up only a small slice of everything that actually exists. The rest is dark matter and dark energy, two of the biggest unsolved problems in modern physics, and we still don't know what either one actually is. Rubin is designed to map dark matter indirectly by measuring how its gravity bends and distorts the light coming from distant galaxies, a subtle warping effect scattered across huge areas of sky. Do that across billions of galaxies and you start to get something science has never really had before: an actual map of where the invisible mass of the universe is sitting. It's also expected to help track the effects of dark energy, the mysterious force that's accelerating the expansion of space itself. By observing how galaxies are distributed and moving across billions of years of cosmic history. Fittingly, the observatory is named after Vera Rubin, the astronomer whose work in the 1970s provided some of the first strong evidence that galaxies contain far more mass than we can actually see with a telescope. The discovery that effectively launched modern dark matter research. Decades later, The instrument carrying her name may end up producing the most detailed map ever made of exactly the kind of invisible structure she first found evidence for. Here's the part that should genuinely unsettle you. Everything described in this video happened before Rubin's real 10-year survey had even fully started. This was the observatory clearing its throat. Already, in that short window, it turned up a stellar stream wider than our galaxy that nobody had ever catalogued. Over 11,000 new asteroids, including one that appears to be breaking the rules of physics just by staying in one piece. A candidate for a star that vanished into a black hole without a single flash of light. And the very real possibility of catching visitors from other solar systems passing silently through our own. So ask yourself the obvious question, and then what happens after one full year of this? 5 years? The full 10? How many more stars are going to quietly disappear in the data with nobody watching in real time to notice? How many black holes have already formed in total silence, scattered across the galaxy, with no explosion to mark the moment of their birth? How many interstellar objects have already drifted through our solar system, completely undetected, simply because nothing was watching closely enough to catch them? For most of human history, we looked up and saw stillness, a sky that felt fixed, eternal, unchanging. Rubin isn't giving us a sharper picture of that sky. It's giving the sky a memory. And once you can compare what's there now to what was there before, the universe stops looking like a photograph and starts looking like exactly what it's always been. Something violent, restless, and constantly in motion. We just finally built something capable of catching it. There's a broader shift buried in all of this that's easy to miss if you only focus on the individual discoveries. Astronomy has spent most of its history being reactive. A supernova goes off and telescopes swing toward it. A comet is spotted and observatories scramble to track it before it moves on. Discovery, for the most part, depended on something dramatic enough to catch our attention first. Rubin flips that relationship. It isn't waiting for the universe to announce itself. It's checking in on everything, constantly, whether anything dramatic is happening or not. Which means the discoveries aren't going to stop being unusual. If anything, the early data suggest the opposite. The more consistently you watch the sky, the stranger it turns out to be. That's the real reason scientists keep describing these first few months as unsettling rather than simply exciting. An asteroid that shouldn't hold together. A stream of stars the size of a galaxy that nobody had mapped. A star that may have died without a sound. None of these are anomalies in the sense of being mistakes or glitches. They're evidence that the standard picture of a calm, predictable universe was always incomplete. We didn't have the tool to see how incomplete it was until now. And the survey is only a few months into a planned decade of operation. Every one of the numbers in this video, the asteroid counts, the galaxy tallies, the potential interstellar visitors, is the smallest version of itself that it will ever be. They only grow from here, which means everything that felt overwhelming about this first release of data is, by design, about to happen again and again at a scale that gets larger with every passing year. So the next time you look up at a clear night sky and it looks calm, remember that somewhere in Chile, a telescope the size of a small building is looking at that same sky and quietly building a list of everything that just changed. If this kind of deep space discovery is the reason you're on this channel, make sure you're subscribed, because we track findings like this the moment they surface, not months later once everyone else has already covered it. Drop a comment with which discovery from this video unsettled you the most, and we'll see you in the next one.